All right, we're up and going. Get volume. Cool. Well, welcome back. So, let's start with any questions. So, I'm planning to continue today talking about taking truth tables, turning them into equations using sum of products. And I want to move quickly to talking about minimizing these equations, trying to simplify them in a systematic way, and then dig more into product of sums, and then take a look at exclusive ORs, because they're kind of an outlier in digital logic, but they turn out to be very useful for some things we'll be doing in the next lab. So we'll look at XORs, and then go on from there. So, any questions about anything you want to talk about up front? Homework, lab, general concepts, anything at all?
Yeah, I have a question about the homework.
Okay.
So for question 3, I noticed that there are 4 variables there, and are we? In the example, you do put a truth table, but I just want to clarify: we do need to put a truth table in for question number 3.
If you can convert this to a canonical product of sums and sum of products without a truth table, that's perfectly fine. And there's ways to do that. If you don't know how to do that, the easiest way is to write a truth table, though. But the goal here is that at the end, you have an expression that will look something like this. F of A3, A2, A1, A0 equals something plus something plus something plus something, where each of these are just, a product expression, which may have, A3 or A3 bar, A2 or A2 bar, A1 or A1 bar, A0 or A1 bar, right? That would be a sum of products, and then a product of sums would be something plus something plus something plus something times something plus something plus something plus something times, etc. Product of sums. So each of these is either A3 or A3 bar, A2 or A2 bar, A1, A1 bar, A0, A0 bar. Does that make sense?
Yeah. Okay.
Okay, cool. All right, other questions? All right, good deal. Let's keep talking about sum of products, and then let's look at how to minimize expressions. So as a reminder, let's suppose we have 3 input variables, A, B, C. And at this point, you really, really want to be writing your truth tables in the following order. Now, technically, the truth table is correct, whatever order you put these rows in, as long as the output value corresponds to the combination of inputs. But anybody who reads a truth table that you've written is going to expect them to be in this order, and a lot of times they're not even going to look at the inputs in particular. They're going to assume the first one is 0, 0, 0, the last one is 1, 1, 1. And what we do with minimizing equations, if you always do these in the same order, in particular in the same order that everybody else does and that we do in class, it will speed up how you do some of the mechanics of simplifying equations, looking at truth tables and converting them into sum of products and so on. So I'm going to start kind of insisting that when you write a truth table, do it in this order. And this is the order where if you converted each of these numbers to an integer, you would get 0, 1, 2, 3, 4, 5, 6, 7. So if you're not sure how to write this order, go ahead and ask now or ask in office or lab hours or something. But this was this trick of write a 0, 1, and then repeat the pattern and add another digit, zeros on top, ones on bottom. And then take this pattern of 4 bits, repeat it down here, put zeros on the top, ones on the bottom, and you can keep expanding out to however many bits you need. So if we have an equation like this, we know that we can write a sum of products by looking at each point where we have a 1 in the output function. And so we could say f of a, b, c equals, and we can write a product term for each combination of inputs that gives us a 1. So the rule for writing the product term is if there's a 0 in the input variable, put a bar on top. If there's a 1, don't put a bar. And then OR all of these product terms. So the second term here would be a bar b, c. This third term would be a b bar c, and this fourth term would be a b c. And so we can always do this, and one of the things we talked about on Monday was this idea that we can write these abbreviations that we call min terms, and this is where the order of the rows becomes important. We can write these abbreviations called min terms to represent these expressions. So we could also say, f of a, b, c equals, and this we can just say m2, and for this term we can say m3, and m2 means a bar b, c bar, m3 means a bar b, c, and so this gives us exactly the same information that we had here. And if we're doing a sum of products, we know that there's a sum in here, and we know that since we want products, we're going to have min terms, and so we can also write this in a more compact form as just sum 2, 3, 5, 7, either prime. So that's kind of where we left things with sum of products on Monday. Any questions about getting to this or these expressions up here?
Could you please explain the difference between the sum of sign and the pi? So the sum of is for min terms?
So the sum of is saying take these min terms and put plus signs in between, add them up. The pi is saying let's do a product. So if we did a product of max terms, this would be m0 times m5. So the product says put a AND operation between these. The sum says put an OR operation between these. And each of these max terms, for example, max term 0 turns out to be A or B or C. And max term 5 turns out to be A bar or B or C bar. And so this is a product of two things that are themselves sums. So this is a product of sums expression. This is a sum of products. So the pi is just the multiplicative version of the summation, which is the additive version. Multiplicative is a hard word at 8 a.m.
Thank you.
You're welcome. All right, so you've got a truth table. You're trying to build a circuit. You come up with a set of equations. This equation is going to be pretty cumbersome to turn into a circuit because I'm going to require 4 AND gates. So 4 ANDs. Thank you. And those are 3 inputs each. And then I'm going to need a four input OR gate. And AND gates with 4 inputs are pretty expensive. Good morning. And OR gates with 4 inputs are pretty expensive. And sometimes you don't have a 3-input AND gate. Sometimes all you have is 2 input gates. And so if I want to do something like A bar, B, C bar, what I might need to do is take 2 of these and AND them together, and then take that result and AND it with C bar. And so each of these might require 2 AND gates. That's 8 AND gates. And my 4-input OR, well, I might need 3 OR gates to do that. So I'm up to 11 gates that I need. And so you start getting more chips, you get more wiring, you get more power, you get more chance of failure, you get a larger physical size, you might need a bigger proto board. And in general, when we're building circuits, we'd like to make things as simple as possible, but no simpler, right? Einstein. So if we look at this equation algebraically, we may see ways to rewrite it that end up giving us a simpler circuit. So let me put this down up here. So we've got A bar, B, C bar, or A bar, B, C, or A, B bar, C, or A, B, C. And let me pull up our textbook, assuming I've got a copy of it somewhere. I don't know if this is the latest edition or not, but it will be close. So in your textbook, there's Boolean algebra theorems, page 38. And in here you find some of these things we talked about the first week, some of the review from 120, some new stuff. Things that are true in Boolean algebra. For example, if we take x and we negate it twice, we end up with x. If we take x and OR it with itself, we get x. And if we take x and we AND it with 0, we get x. And we have cool fancy names for these things: the idempotency theorem, the double complementation theorem, absorption theorem, things like that. Using some of these ideas, we can take equations such as this and potentially simplify it. So any inklings of anything we might be able to do here that might give us a simpler expression, or at least a different expression. Any thoughts?
We combine like terms.
Hmm.
A naught plus A naught is still A naught.
We could combine terms. So we can somewhat think of this like a plain old algebraic expression, where A bar is a variable, B is a variable, C bar is a variable. And a lot of what we do in traditional algebra still works in Boolean algebra. Some things don't. But combining terms is something that'll generally work the same. So is factoring. That's how we combine terms. So I have A bar, B, C bar. I have A bar, B, C. This A bar, B is common to both of these expressions. So I can factor out that A bar B and end up with C bar or C, right? This product, A bar B C bar, that's this term. And this product, A bar B C, that's the second term. And over here on the right, I have AC in common with both of these. And I know I can rearrange the order of these things, right? That's commutativity. So yeah, factor out a common term and simplify from there. So a common term between these two pieces of the expression would be AC. And here we have a B bar. And here we have a B. AC B bar is this term, and ACB is that term. So this equation should have the same truth values as this equation. Alright, anything I can do further on this equation to make it even simpler?
If it's C naught plus C, it can be either or. So you don't really need both.
Mm-hmm. So let's take a look at C naught or C. C has got to be either 0 or 1. It's either false or true. So if C is 0, what is C naught?
The opposite.
Yeah, so it's a 1. What is 0 ORed with 1? Today is Sunday or today is Wednesday. What's the truth value of that statement?
1.
That's a 1. There's a fancy name for that. It's worth it because you can toss it out if you're stuck with, come up with an answer to a different question. X or... Oh, there isn't listed here. Oh, it's not listed here. Oh well. We'll make up some fancy name. We'll call that the green frog theorem. So C or C bar is equal to 1. If C is 1, C bar is 0. 1 or 0, that's again 1. So as several people have said in chat, C bar or C is equivalent to 1. So this is equal to A bar B and 1. And this is equivalent to AC, and same thing, B bar or B is equal to 1. And if we take anything and we AND it with 1, we just get back that original thing. Right, so 0 ANDed with 1 is 0, 1 ANDed with 1 is 1. So this is A bar B, and this is AC. Well, hey, we took this original circuit that needed, several gates, maybe 11 gates, and we've changed it to something that needs 2 AND gates and an OR gate, and maybe an inverter. So there's A, B, here's C and A, and we AND those, and here's A bar and B, and we AND those. And we put those through an OR gate. Bingo, we're done. So it's worth the time and effort to when we have an equation from a truth table, before we try to make a circuit diagram, it's worth it to try to simplify it, right? Except for the first 2 circuit diagrams in Lab 3, which you're told not to simplify, so you don't get to do this for that, but you get to do it for the final circuit diagram. And in general, this is something we want to do, right? We want to use fewer parts, we want to use simpler parts, smaller parts, and so on. All right, let me do a little sidebar here and go through what I just did to come up with this, because on Lab 2 it looked like there was some confusion about if you have an equation that you want to implement, how do you actually come up with a circuit for it? And this OR gate is important here. So let's take a little sidebar from simplification and talk about once you have the equation you're going to build, how do you sketch a circuit diagram for it? And I'm not worrying about pin numbers, part numbers. I'm just worrying about this logic diagram because that's the first part of getting to a full schematic. So let's go back to our original equation because it's a nice complex. A bar B C bar, or A bar B C, or A B bar C, or A B C. So I'm going to talk about how to sketch this equation as it is, and then we'll come back and we'll look at the simplification business and make that mechanical. So there was a technique that we went through earlier, which was take your input variables, run them vertically, like this. Take each of them, put it through an inverter, run that inverted version vertically. And this works great if you have a sum of products. So in this case, I know that I need to calculate a product or an AND of A bar, B, and C bar. And so I can take A bar, B, C bar, calculate their product. I also need to calculate A bar, B, C, so I can take A bar, B, and C, calculate that product. And you just keep going. All of your product terms, just find which inputs you want and them together. So A, B bar, C, and finally A, B, C. So now I have my 4 AND terms, my products, and I need to take the OR of those. So I'm going to take these and feed them into a 4-input OR gate, like this. And there's my output, F of A, B, C. And then if you like, you can go back and clean up these stray lines, but they don't actually do any harm. And in this kind of drawing, it's not unusual to see those, extended lines there. That's totally fine. But now, I've got a pretty well laid out diagram that's pretty easy to follow, right? When I'm hooking up the inputs to this chip, I know I need one to come from this output, one to come from my switch B, and one to come from the output of this inverter. And this OR gate is important. If I just connect these AND gates together, then I potentially, have a 1 coming out here, a 0 coming out here. That creates something we call bus contention. This is doing everything it can to generate 5 volts on the output. This is doing everything it can to generate 0 volts on the output. If I connect those outputs together, they're going to fight. And the circuit's going to draw a lot of current, and something will give. The power supply will turn off, or the chip will fail or something. So we use the OR gate to combine these. Yeah.
Quick question.
Mm-hmm.
I don't believe there's a 4-input OR gate.
Mm-hmm.
What would we do instead?
So if you don't have a 4-input OR gate, you can take 2 inputs and OR them, take 2 inputs and OR them, and take the output and OR those. So if we call this WXYZ, this is WX, this is YZ, and this is WX, sorry, these are ORs, this is W or X ORed with Y or Z. And we have some rules that say the parentheses don't matter, and so this is W or X or Y or Z. Another option would be to take WX, OR those, take this, OR it with Y, take that result, OR it with Z. Which gives you this algebraic expression, which again, if you use the rules of associativity, we can get rid of the parentheses, we'll end up with exactly this. So different ways to do it. Which of these circuits do you think is better to use, though? Is there a difference? No preference? I'm just looking for ideas here.
I think the top one would be more easy to use it, wasn't it?
Yeah, the top one, I mean it's got some symmetry to it, which is nice for some way. It's probably less likely to get wired incorrectly. The other thing is it's potentially going to be faster. Because if W changes, that change has got to go through this gate, and through this gate, and through this gate, potentially until it affects the output. Whereas here, any input change is going to have to go through 1, 2 gates. So next week we're going to start looking at timing issues. We're going to see how long it takes for these gates to respond. And we'll see very clearly that this circuit is generally going to operate faster than that circuit. And speed is usually important to us. But functionally, as far as the logical behavior of the output in terms of the inputs, these are exactly the same. All right, so if you weren't able to come up with a correct circuit diagram for Lab 2 for the traffic light controller, hopefully that helps. If it doesn't, definitely come by lab hours today, or ask now, right? Either ask for more clarification now, or come by lab hours tonight, 5 to 8, and make sure you know how to do that, because in Lab 3 you're doing 3 versions of your circuit for the traffic light, right? 2 of them are going to be extremely complex, because you don't get to simplify, and then the third one you're going to simplify. All right, so let's go back to simplifying our equation. And let me go back to this original expression we were working with. And the truth table looked like this. And if we just kind of look at the set of terms here in the truth table, we can make an observation. So this is saying what the output should be for this combination of inputs. This is the output for that combination of inputs. Because these 2 rows are adjacent to each other, right next to each other, we can observe the following thing. This combination of inputs and that combination of inputs are almost the same. For both of these, A should be a 0, B should be a 1. But here we've got C as a 0, C as a 1. We can reimagine that in terms of what we call a don't care. And we can say as long as A equals 0 and B equals 1, we don't care what the value of C is. If C ends up being a 0, our output should be 1. If C happens to be a 1, our output should still be a 1. So the only thing we need to know that one of these outputs, should be a 1 is to observe that A is equal to 0 and B is equal to 1. And so that lets us say, hey, let's write, A bar B. If this expression is true, then our output should be 1. Because if this is true, we're either in this row or this row, and it doesn't matter to us which of those 2 rows we're in, because both of those rows should output a 1. So this is a different way to see that we could write a simplified expression involving just A bar B as one of our terms. Well, if you're good at rearranging things in your mind and seeing patterns that are a little more deeply hidden, you might look at this row right here and this row right here and make a similar observation, which is, hey, both of these rows should output a 1, and in both of these, A is a 1 and C is a 1, and B doesn't matter. As long as A is 1 and B is C is 1, we want the output of our circuit to be a 1. Here's a 1 and a 1, B is a 0, I don't care about that. Here's a 1 and a 1, B is a 1, I don't care about that. As long as A and C are both 1, we want the output to be 1. And so A equals 1, C equals 1, that's a product term, just A ANDed with C. And if this expression is true, then we want the output to be a 1. So this simplified expression covers these two 1s. This expression covers these two 1s. If we OR those, that should give us an equivalent version of our output function f, A bar B or AC. That's what we got over here algebraically. So sometimes by looking at the truth table, we can simplify our equations without having to do a bunch of algebra. And it works really nicely when you have two 1s in adjacent rows like this. If we had two 1s right here, if we had two 1s right here or here, we can do this simplification. Now it doesn't work if, for example, we have a 1 here and here, because between these two rows we have two inputs changing, right? So we know we want A to be a 0, but B and C have to be the opposite of each other, so that doesn't work. But these two, these two, these two, these two, anytime that they're both 1s, we can do the simplification. And this is called the adjacency theorem. The adjacency theorem says xy or xy bar equals x. That's that algebraic thing we did a few minutes ago, where we factored out the x and we said this is the same as x ANDed with y or y bar, which is just a 1. It's called the adjacency theorem because it relates to how we can simplify a truth table when two rows are adjacent to each other. Is everybody still here? So all of this is just motivation for what we're going to do next, which is called a K-map. Let me give you one more aspect of this truth table approach to simplifying. These two outputs of 1 were easy to simplify once we know the trick, because they're right next to each other. And we can really quickly see, hey, make this a 0, make this a 1, don't worry about C. That's great. These two, not so easy, right? You have to sort of look around and find this deeper pattern. Hey, that's a 1, that's a 1, the 0 doesn't matter. No problem. But if we had decided to write our truth table a little differently, like this, so I'm going to write exactly the same truth table, but I've rearranged my columns because, I don't know, I got distracted when I was writing ABC and it came out ACB. Look what happens when I fill in these two 1s right here. A is a 1, C is a 1, B is a 0. That's this row right here. A is a 1, C is a 1, B is a 0. That should be a 1. And this last row, 1, 1, 1, is right here. Guess what? I'm back in this delightful situation where I have two rows right next to each other, adjacent to each other, that should both be 1s. And again, it jumps out at us, hey, you know, A and C should be 1, B doesn't matter. And so if I just write AC, that's an expression that's true exactly when the output should be 1. So if we were to rearrange the columns in all sorts of different ways, all we would have to do is figure out each time that we have two 1s adjacent to each other, and we can immediately start eliminating variables. All right, well, there's a way to do this, and this way is called a K-map. I'll try to spell Karnauugh Map. Might be misspelled. Well, there's definitely not two U's. That's just a typo. But a Karnauugh Map, or a K-map, is a systematic way that we can do this kind of simplification. All right, so this is going to be a fairly long, very detailed procedure. And we'll go through this a bunch of times. We're going to do a bunch of examples. We're going to start with a function with 3 inputs, this function, and then we're going to look at a function with 4 inputs. And we're going to get a lot of practice with this. You have one homework question in the current set, and you're going to do this a bunch for the rest of the course. So this is just a first introduction to a K-map. And so stick with me. And so we have 3 input variables. So we're going to draw a picture of a rectangle. And we're going to stick with powers of 2 for a lot of things. So powers of 2 are 1, 2, 4, 8, 16. Keep those in mind. And I'm going to put a little line here. And I'm going to label this side A, B, and I'm going to label that side C. And my goal is to write along here on the side all possible combinations of A, B, and to write here all possible combinations of C. And C is pretty straightforward. Bye, have a good day. I'll see you this afternoon. Bye. C is pretty straightforward, right? C has got to be either a 0 or a 1. And AB, there's 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. All right, so here's the first really important thing. Watch the ordering that I'm going to use when I write down the values of AB. I'm going to do 0, 0, 0, 1, but the next thing I'm going to write 1, 1, and then 1, 0. That's different from the usual way we write 2-bit numbers, 0, 0, 0, 1, 1, 0, 1, 1. We have to use this special ordering. Another day, we'll talk about something called a gray code. And a gray code is a sequence of bit patterns It's a sequence of bit patterns where from one pattern to the next only a single bit changes. And normally when we count in binary, for example from 001 to 010, we have 2 bits changing. From 011 to 100, we have 1, 2, 3 bits changing. But with a gray code, when you move from one pattern to the next, only a single bit changes. And if we went back from here to the beginning, we'd still only have a single bit changing. So we're writing the numbers over here in gray code. And you can just memorize this, right? 0001, 1110. That's always the order we're going to write these in. All right, and now we're going to fill in the ones. So let me start a table over here. I'll call this making a K-map. So step 1 is draw your rectangles and label. And add the zeros and ones to the side and top. And watch the order. Alright, second thing we're going to do is fill in the ones. And we're always working with a truth table. Right, our goal is to simplify an equation from a truth table. So given your truth table, we're going to fill in the ones. So let's go back to our very cluttered looking original truth table. And we have 4 ones in here. The first is for the inputs 0, 1, 0. So let's find that input. 0, 1, 0. So A is a 0, B is a 1, C is a 0. We want a 1 right there. The second one is A is a 0, B is a 1, C is a 1. So A is 0, B is 1, C is 1. There's a 1 right there. Our third input is 1, 0, 1. So here's 1, 0, 1. And our fourth input is 1, 1, 1, which is right here. Alright, so that's the second step. Fill in the ones from the truth table. Third step is what we call covering your ones. So what does this mean? We're going to cover these with rectangles. We're going to draw boxes around groups of ones. And we have to follow a set of rules. So the first rule is each rectangle has to be either 1, 2, or 4 by either 1, 2, or 4. We can't draw a 1 by 3 rectangle. We're not allowed to draw one rectangle around all 3 of these ones. So your rectangles, each side has to be either 1, 2, or 4 in length. Cover. Ultimately, we need to cover all the ones. We're not allowed to cover any zeros. So there's zeros in the boxes we haven't filled in, but usually we don't fill those in. We just fill the ones. So we're going to try to write rectangles to cover up these ones. The rectangles have to have sides which are 1, 2, or 4 in length, and we're not allowed to cover any zeros. So cover all the ones, don't cover any zeros. It's okay to cover a 1 more than once. And bigger rectangles are better. And fewer rectangles are better. And your covering may not be unique. Or it may be unique. Sometimes there's more than one way to satisfy all of these rules. And so what's an example of rectangles I could use to cover these ones? Well, I could put a 1 by 2 rectangle here, and I could put a 2 by 1 rectangle there. And that's a great covering of the ones in this K-map. I've got every one covered. I don't have any zeros covered. My rectangles have legal dimensions. I used 2 rectangles that were, sort of big. That's a great covering. Now, I could have said, I'm going to draw a 1 by 1 rectangle here, 1 by 1 rectangle here. That's not as good a covering. Why? Because we want fewer rectangles and we want bigger rectangles. Well, here I had 3 rectangles. Before I had 2. That's better. Here, 2 of my rectangles were just little 1 by 1s, whereas here, all of my rectangles are 1 by 2 or 2 by 1, they're bigger. So this is a better covering. I could draw another rectangle here. That's fine because I'm allowed to cover my ones more than once, but that would end up with 3 rectangles. Fewer rectangles are better. So this is the optimal covering of the ones in this K-map. And it's a unique best solution in this case. Alright, and I'll come back and add one more rule in a few minutes. Fourth step, write a product term for each rectangle. And then the fifth step is just to sum those terms. And we're done. We'll have a minimized equation for our original truth table. Alright, so how do we write the product term for each rectangle? Let's just look at this first rectangle here. And what you want to do is consider each square in that rectangle and see what happens to your input variables. So just looking at this one up here, in this box the value of a is 0, in this box the value of a is 0. And so everywhere in this rectangle a is equal to 0. Alright, let's look at b. In this box b is a 1, in that box b is a 1. So everywhere in this rectangle b is a 1. And finally, let's look at C. In this box, C is a 0. In this box, C is a 1. And so we say C does not matter. So taking that information, we can write a product term the same way we wrote terms in our truth table. Since A is a 0, I'm going to write A bar. Since B is a 1, I'm going to write B. Since C doesn't matter, I'm going to ignore C. I'm going to AND these two things together. This is the product term corresponding to this rectangle. So writing the product term for each rectangle, see if variable equals 1, 0, or both. If it's a 1, then write the variable. If it's a 0, write the variable with a bar. If it's both, don't use the variable at all. So let's look at this rectangle down here. What does A do everywhere in this rectangle? Is it 1, 0, or both? A is a 1. What about B? It's both, so B does not matter. And what about C?
It's 1.
C is a 1. Alright, because here C is a 1, and here C is a 1. And so now we write the product term corresponding to A equals 1, C equals 1. It's just A ANDed with C. And now to write the final simplified equation for our original truth table, we take those two product terms and we just sum them together. A bar B or AC, and that's our simplified equation. Alright, that's how you use a K-map. And it's always just the same sequence of steps. And so we're going to go through a bunch of examples of this. So let me make a different truth table. And let's switch to 4 input variables. So you get to watch me write a bunch of zeros and ones now. And I'm writing in pen, and I'm going to use pencil so I can reuse this. All right, so there's the truth table. And I'm just going to kind of make up some values that I think will be interesting. All right, there's a semi-random truth table. And I'll keep our instructions over here on the side. And let's make a K-map. So the first step is to draw a rectangle, label, add the zeros and ones to the side and the top, being careful of the ordering of the ones and zeros. So I'm going to make in pen a 4x4 K-map. Now if my truth table is A, B, C, D, here's the order I'm going to use for my variables. I'm going to put A, B over here and C, D up here. And since I have two variables running vertically, I'm going to have 2 squared or 4 rows. And since I have two variables running horizontally, I'm going to have 4 columns. And so I've got 16 squares, which goes along with the 16 rows of my truth table. And I'm going to label these 0, 0, 0, 1. Here's the tricky gray code, 1, 1, 1, 0. And same thing going across, 0, 0, 0, 1, 1, 1, 1, 0. All right. So there's the rectangle. Next step, fill in the ones from the truth table. So I'm just going to look where I have a 1. 0, 0, 0, 1. So A is 0, B is 0, C is 0, D is 1. That's going to go right here. 0, 0, 1, 1. That's going to go right here. 0, 1, 1, 0. Well, 0, 1, 1, 0 is over here. And 0, 1, 1, 1. That's right here. 1, 0, 0, 0. 1, 0, 0, 0 is right here. 1, 0, 0, 1 is right there. 1, 0, 1, 1 is right here. And then 2 more ones. 1, 1, 0, 0. And 1, 1, 0, 1. So this is the first challenging part of doing a K-map, is filling in these ones from the truth table. But after you do this a few times, you'll find patterns. And I don't want to teach the patterns, because then you're just following a set of steps for no reason. I want to make sure you understand that there's a 1 here, because this box corresponds to A equals 0, B equals 0, C equals 0, D equals 1. And in that combination of inputs, there's a 1 in the output. But eventually, you'll come down to where you can just fill in this truth table into this K-map by saying this is the first, second, third, fourth row, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And once you know that pattern, you don't have to think about, well, 1, 1, 0, 1 is over here. You can really just sort of read through this and write the ones into the right spots. So this becomes a very quick step once you practice it. All right, so that's the long mechanical part, and then the fun creative part, covering your ones with rectangles. So you know the rules, right? We got to cover all the ones, none of the zeros. We can do multiple covers. We want bigger, fewer rectangles if possible. And the rectangles have to be 1, 2, or 4 on each side. So any suggestions for some rectangles I can draw to cover the ones in this K-map?
Bottom 3.
These?
Yeah.
So that would be a good choice other than this one nagging rule of each side of the rectangle has to be either 1, 2, or 4. And so 3 is actually not allowed. But there is something close to that we could do.
You could do the bottom 4.
Yeah, we got a big 2x2 rectangle here. If you see a 2x2 rectangle, get excited. This is going to make life good. The bigger the rectangles, the simpler the equation you'll end up with. So yeah, 2x2 at the bottom, good. Alright, what else could we do? And this is like, you know, a word hunt or a Sudoku or something like that. You'll develop approaches to figuring out how to do this, but just kind of looking at the top of my head right now, one thing my brain is doing is looking for ones that are by themselves. Right? This thing right here, I know I could cover this like that or like that. I've got choices there. But this one is kind of by itself. The only thing I can do to cover this is go like this or go like this. So I'm going to go ahead and grab those top two, like some people said in chat, and cover those. Alright, great. What else? Now I can't do a 2x2 here because I'd be covering a 0. And we're not allowed to cover zeros. But I could do a 2x1 underneath it. Excellent. Alright, and then we've got one rectangle down here by itself. We can do a 1x1 to cover that. So this is where this last rule comes in, which we call asteroids model. So how many people here have played asteroids? If not, you need to find a version of this game and play it. So asteroids, you've got this little ship flying around and you're in the middle and you can turn your ship and you can shoot. Right? Simplest game possible. And your shot goes out and hopefully breaks an asteroid into smaller pieces, and each time you hit a piece it breaks in half. So it's a binary thing, it's like 250. And when you get down to 1/4 of the original size, if you hit that block it disappears. Right, and then you're safe. If the asteroid hits you, you die, and then occasionally a spaceship goes by, and if you hit the spaceship, you get a lot of points, right? This was like, 1980s, so it was a violent time in our history. The cool thing about asteroids was if you went off the top of the screen, you reappeared on the bottom. So it was like a hypergeometry where the top and the bottom were connected, and the right side and the left side were connected. And this was good because when you were hunting for the ship, you just keep going up and you'd wrap around and you'd wait for the ship to appear and then you'd just turn and hit it. So we use an asteroids model with K-maps, which means this bottom edge is connected to the top edge and the left edge is connected to the right. And so even though on this picture this one is sitting by itself, it's actually adjacent to this one up here. And I can draw a broken rectangle 2x1 that looks like this. And so I've covered this one with actually a 2x1 instead of a 1x1 rectangle. And that's the fun, freaky part of K-maps, right? Is trying to imagine this wraparound.
Question.
Yeah.
Never mind.
Okay. All right, so that's the complete set of rules for covering the ones. Don't cover any zeros. You can cover a 1 more than once. Bigger, fewer rectangles are better. And you're allowed to wrap top to bottom, left to right. Which means, for example, I could have covered these two ones with a broken rectangle. Could have gone boom, boom, right? But there's no need to do that. Because I covered this one with this nice 2x2 rectangle. That was my best choice to cover this one and these ones. And if I did another rectangle here and here, I would not get an incorrect result, but I would not get the simplest result. Similarly, I could do another 2 by 1 to cover these two, but I'd get a more complex equation. Alright, so this rectangle down here, let's see what A, B, and C, and D do. So what does A do in this 2 by 2 rectangle? Right? A is equal to 1. There, and there, A is always equal to 1. What about B? Alright, does not matter. B is a 1 up here, B is a 0 down here. So it does not matter. What about C? C is a 0, right? 0, 0, 0, 0. And what about D? C is a 1, a 0. So that does not matter. So the algebraic expression, the product sum corresponding to this rectangle, is based on A equals 1, C equals 0. So that's A, C bar. So you know, our original truth table, we would have had 1, 2, 3, 4, 5, 6, 7, 8, 9 product terms, each with 4 inputs. Well, here we've got a product term with 2 inputs, so we're off to a pretty good start on simplifying this. Let's take a look at this upper rectangle, and I'll go ahead and answer my own questions. So in both of these, A is a 0, and B is a 0, and C is a 0 and a 1 here. So we're going to ignore that, and D is a 1. And so this box represents A is 0, which is A bar, B is 0, which is B bar, and D is 1, which is D. So A bar, B bar, D. And this box, A is a 0, so I'll just go ahead and write A bar. B is a 1, so I'll write B. C looks like a 1 here and here, so I'll write C, and D is a 1 and a 0, D doesn't matter. And then this last broken box here, and I'll write this one out more explicitly. So what does A do in this rectangle that's containing this box and this box? What can we say about A? Say again? Doesn't matter, right? So it's a 0 or a 1, so it doesn't matter. What about B? It's a 0, right? Because here and here, down here, B is a 0. Up here, B is a 0. So B equals 0. And then what about C and D?
Well, C and D are both 1.
Yeah, so here and here, C is a 1. Here and here, D is a 1. So C is a 1, D is a 1. And so this corresponds to the equation B bar CD. And so our overall function is just the sum of these product terms. So it's A C bar or B bar CD or A bar B C or A bar B bar D. And that's a simplified equation which should produce exactly the same truth values as this truth table. And so now instead of having all of these 4 input AND gates with a bunch of inverters and then ORing them together through a 9 input OR gate, right? We got four pretty simple product terms, and we just OR those together. So this is a great time saver, energy saver. And I believe this is the simplest we can get. And I think it's probably unique. Certainly this is got to be part of our solution. We can only cover that one with this or that. And if we do this, then we would need to cover that one. No, it's not unique actually. It is simplest. But we could have covered this one with a broken rectangle like that, and then covered this with a broken rectangle and covered that like we did. So we could have found an equally simplified but different version of F. Alright, so I'll leave those rules up. Let's go ahead and take a break, and let's come back in, let's see, let's come back in about 4 minutes. And we'll just keep doing some more examples of this, and we'll dig into some different ways that these maps can end up looking. And then we'll talk about product of sums. We're going to talk about don't cares also. So we're going to add a little bit to this set of rules. All right, so we'll be back in about 4 minutes. something fun or work?
Not fun.
Oh.
But I finished the ODP and I got 10 out of 10. Woo.
Awesome. Good job.
Do you need anything from the store? Or want anything?
Cow caviar. Star daydream. Maybe mozzarella cheese.
Low fat.
Preferably not low fat, but that's
But
all
if
they
they
have.
have it.
Whole milk is better, but if not,
The shredded white.
yeah. Mid part skim, yucky yuck.
Are we good on sauce?
I think we're good on sauce.
Okay.
Could use my pretzel, but I don't want you to be in there for a long time.
I won't. I got very little to get.
Okay.
It's very targeted. I'm getting more carrots.
Yeah, carrots are good. Chocolate.
Do you need chocolate?
Yeah, go ahead now. I see one juice.
One what? Juice? Oh, yeah, juice.
No, you don't have to get it from there. We can order it. All right, I'm back. All right. So questions so far?
It makes sense for the most part.
Okay. It's really just kind of an algorithm, but it's not an intuitive algorithm, and so that can make it a little tricky. All right, so let me add one more embellishment, which is don't cares. And a don't care is an optional cover. So what does a don't care mean? Sometimes, usually when you write a truth table, your outputs are all ones or zeros, but sometimes we don't care what an output is for a particular input combination. So it may be that this value right here, if all of your inputs are 1, we don't care what the output is. And so we could write that as a dash. And a dash means we don't care. Okay, why might we not care? Because maybe our inputs are coming in such a way that we never expect all 4 of these inputs to be 1. So if you have a traffic light controller, I can't think of an example like that. But maybe for whatever reason, right, we've got 4 things going into a system. Maybe it's just not possible that all 4 of these inputs are going to be 1. Because maybe this means, somebody's at the front door, somebody's at the back door, somebody's at the side door, and nobody is at any of the doors, right? And so we could not have somebody at all 3 doors and also at none of the doors. So this combination would never appear. And so we can put these dashes or don't cares into our truth table. And when we make our K-maps, we go ahead and we enter in the don't cares. So fill in the ones from the truth table and the don't cares. So in this case, we've got a don't care in that 1, 1, 1, 1 position, which is sitting right here. And then when we cover our ones, cover the ones with rectangles, we can optionally cover the dashes. We don't have to. But if using a dash gives us fewer rectangles or bigger rectangles, we're going to go ahead and do it. Right? Our goal is to satisfy this metric, bigger rectangles, fewer rectangles. If putting in a dash helps us, go ahead and put in the dash. If it doesn't help us, don't bother. So suppose we have, let's put a dash in here also. So maybe this is another don't care, 0, 1, 0, 0. So 0, 1, 0, 0 is right here, so there's a dash right there, and there's a dash here. All right. So go back to the original question of covering our ones, right? Does anyone see a different covering we could do that might give us bigger rectangles or fewer rectangles by possibly covering a dash?
Instead of wrapping around, we could move that up and make a 4 piece.
Ah, we could do all 4 of these with a single 4x1 rectangle. And that's glorious. Anytime you see 2x2, 4x1, 1x4, get happy, right? Because you're going to get a really simple expression out. So if I'm covering all 4 of these, what's the expression look like for this? So A could be a 0 or a 1. So A doesn't matter. B could be a 0 or a 1 or a 1 or a 0, so B doesn't matter. C is a 1, D is a 1. This whole 1x4 rectangle is just the expression CD. And so now we get a simpler expression, which is this lower 2x2 rectangle, AC bar. This 4x1 rectangle, which is CD. This little 1x2 rectangle again, which is A bar, B bar, D, and this little 1x2 rectangle, which is A bar, B, C. And so we've simplified our equation. This looks exactly like this, except we got rid of that B bar. And so here, instead of a 3-input AND gate, we can get away with a 2-input AND gate. And this dash over here doesn't really help us. We could cover, you know, a 2x1 rectangle like that to pick up this 1, or we could continue to pick it up with this. But this doesn't really get us a simpler solution. And, you know, we could cover it like that or like that, but we don't want to include it if it makes the solution more complex. Let's see. Why would there be a dash in the truth table? So my kind of weak example was, you know, maybe we've got door sensors. Or let's do car sensors, right? So here's a car on lane A, here's a car on lane B, here's a car on lane C, and here's the citywide disaster alert input, which when there's a citywide disaster, this variable is a 1, and it means there's no traffic on the roads anywhere. So really, any time that this input was a 1, we probably wouldn't care about A, B, and C. And so we'd probably have a lot of dashes in here. It's kind of a goofy example. Sometimes our inputs A, B, C, D are going to represent a decimal number between 0 and 9. And so we would never expect any of these combinations of inputs to appear. And so all of these might be dashes. And that's a real world example that we'll play with in a future lab. Is having a bigger rectangle better if it won't change the total number of rectangles? Definitely. If you can get bigger rectangles, that's good. If you can get fewer rectangles, that's good. And having a bigger one will not increase the number of rectangles. If it doesn't decrease it, that's okay. Bigger is still better. And so why do we have this metric? Why is bigger better? The more ones we have in here, the fewer terms are important, right? So a rectangle with 4 ones, 2 of our inputs are not going to matter. And so we're going to end up with a product term with just 2 variables in it. Here it was AC bar, here it was CD. If you only have 2 things in your rectangle, you end up with 3 product terms. A bar, B bar, D, for example. If you only had 1 thing in your rectangle, you're going to end up with a min term. For example, if I just covered this single 1, it would be A bar, B, C, D bar. So you'd have 4 things in your product term. So the bigger the rectangle, the simpler the AND gate. And then the number of rectangles, that's how many things you have to OR, so the simpler the OR gate. Alright, so that's the deal with don't cares. So on the homework, what have we covered? So there's one question that has you do a K-map. So obtain the product terms of P1, P2, and P3. I'm looking at question 8 here. In the following figure, and verify that each product term evaluates to 1 for its respective input combinations. So you're given a K-map for a function of 3 inputs, x, y, z, and they want you to write down the product term corresponding to this rectangle, which is an ellipse, this rectangle, and this broken rectangle at the bottom. And so this is what we've been doing, right? So in the solved example, for example, this first rectangle, x can be 0 or 1, so x doesn't figure in. Y should be a 0, z should be a 0. So this first rectangle is y bar, z bar. And the text, since it's hard to typeset bars on top of letters, uses an apostrophe after a variable to say y bar, z bar, and so on. And then how do you verify that each product term evaluates to 1 for its respective input combinations? Well, set x equal to 0, y equal to 0, z equal to 0. What is y bar, z bar? It's a 1. Set x equal to 1, y and z equal to 0. What is y bar, z bar? It's a 1. And then your final expression would be the sum of these. So it would be the product you got for P1 plus the product for P2 plus the product for P3. So it looks like this. So same deal here, just different coverings of rectangles. And then question 9, it says in Canvas to skip. So we're not doing question 9 because we're not talking about prime implicants. And then question 10, using a K-map, obtain the minimum product of sums. So we're going to talk about product of sums from K-maps next. But it's going to be a dual process. We're going to cover the zeros instead of the ones, and we're going to write sum terms instead of product terms. But the other rules will be the same. And then 11, it said to only do 11 using the K-map, not using SAR. SAR is a systematic algebraic reduction process, which we're not going to go over. So 11, you're just supposed to find a minimum sum of products using a K-map for this. This expression at the end, MD 9, 11, those are don't cares. So that's worth tagging, right? So this is a compact sum of products. So you want ones in your truth table for min terms 0, 4, 5, 7, etc. And you want don't cares for terms 9 and 11. And make sure you use those don't cares because I believe they'll simplify your equation in the end. So it's a good idea when you're typesetting to put the period in, because it's possible that some authors might put an apostrophe in front of a variable to negate it. And so if you wrote something like this, right, if you're doing this on paper, which is what I strongly recommend, you just write A, B bar, C. It's completely unambiguous as long as, you know, there's spaces in between here. If you use apostrophes the way the book is writing, it would look like A, B bar, C. But there might be an author somewhere who would put the apostrophe in front of, and so the periods can resolve a potential ambiguity there. If you're going to use apostrophes, stick to what the book's doing and put it after, but the periods help you. They're like parentheses basically. But, you know, just do this, write it out by hand, and you're good to go. it's not uncommon in data sheets and literature to see number signs to mean not, and this would be typically written A number sign B C. And so here the number sign is going in front of the variable that's complemented. So again, stick to this. Strongly recommend writing this stuff up by hand. Right? Do it neatly, work logically top to bottom, but don't try to do a K-map, in Word or something like that. You can do it, but unless, you have nothing else that you would rather be doing, it's a whole lot faster to do this, right? If you were writing a formal report, trying to get funding for a project or something, maybe after you figure out your K-map, you would typeset it and have it come out, in a nice computer-generated presentation. But for homeworks, save your time and energy, write it up neatly, and move on. All right, good. Other questions? That should be everything you need for the homework except K-maps on product of sums, which we're going to do next. All right, well, let's move on then. So K-maps for product of sums. So suppose I wanted to do a simplified product of sums for the same truth table. So I'm going to draw my same K-map. I'm going to put two variables along here, two variables along here. I'm going to put them in the same order as I have in the truth table. So this is going to be AB, and this will be CD. I'm going to number these in gray code. And what this is doing is basically rearranging the columns of my truth table into all possible combinations. And as humans, we're not necessarily good at seeing that, hey, this row and this row only differ in this second variable. There's a 1 and a 0 and a 0, and the second variable could be a 0 or a 1. But if we lay these things out visually, that fact translates into the fact that there's two boxes right next to each other. And we're good at visually seeing that pattern. So when we fill in our K-map from our truth table, what we're doing is effectively saying, hey, if these variables were rearranged, these two rows might be right next to each other, and we'd see, 1 0 0 0, 1 1 0 0 0. That second variable doesn't matter. So this is just a systematic way of viewing those properties. All right, so we're going to fill in the zeros instead of the ones. That's the first dual for a product of sums. So this is POS. So 0 0. So 0 0 1 0 goes here and here. I'm going to fill in the don't care still. So that's a don't care. The next term is a 0. These two terms are ones. There's a 0 for 10 10. So 1010 puts a 0 right there. And then there's a 0 for 1110, so 1110 is right here. And there's a don't care for 1111, so there's a dash. All right, so product of sums, this is for sum of products. For product of sums, we're going to fill in the zeros and the don't cares. We're going to cover the zeros, and then we're going to write sum terms for each rectangle, depending on whether the variable is 1 0 or not changing. And then we're going to take the product of those terms. So this will feel like what we do when we write max terms from a truth table. So what are some ways I can cover these zeros?
to bottom right.
Cool. Let's do the top right to the bottom right. So there's a 2 by 1. That's good. There's a lot of choices here. And in the end, I think the remaining choices aren't going to make a big difference. So I could cover these 2 boxes, because I'm allowed to cover the don't care, or I could cover these 2 boxes. Either way, I end up with one more rectangle, and it's got a total area of 2. So I'm going to cover these just because it'll be easier to draw my arrows to that and know what I mean. And then what about these 2 zeros? How can I cover those? Turn the top left into 2 2 by 1s. Perfect. Right? I could certainly cover with a 1 by 1, but I can get a bigger rectangle by going like this. And I'm allowed to cover things more than once. Right? It's okay to cover a 1 or a dash more than once. So I'm going to reuse this don't care and get a 1 by 2 covering here. And there all my zeros are covered. That's a good covering. And now we need to write equations corresponding to these. So let's look at this first rectangle like this. And I'm going to note A equals 0. B doesn't matter. So I'm just going to write an X next to B. C is 0 and D is 0. Alright, so to write a sum term, right, this is like writing max terms. The rule is flipped. If we have a 0, we write the variable without a bar. If we had a 1, we would write the variable with a bar. And we're going to OR these together. So A bar, A or C or D. That's this rectangle here. Alright, this 1 by 2, A is a 0, B is a 1, C is a 0 in both of these, and D could be a 0 or a 1, so D doesn't matter. And so the sum term for this, A is a 0, so it's uncomplemented, B is a 1, so we complement it, and C is uncomplemented. So A or B bar or C. Alright, what about this rectangle, this 1 by 2? Tell me what A, B, C, and D are doing. So looking at this rectangle, so what's the value of A in each of these? Yeah, it's a 1, right? This box right here, A is a 1. This box right here, A is a 1. A is equal to 1. Perfect. What about B? Yep. B is also a 1. It's a 1 right here. It's a 1 right here. What about C? C is a 1 also. What about D? D does not matter because in this box, D, which is this variable right here, is a 1. But in this box, D, which is this variable, is a 0. So D could be a 0 or a 1. D does not matter. So what's the sum expression corresponding to A equals 1, B equals 1, C equals 1?
A naught plus B naught plus C.
You got it. right? If there's a 1, write the variable with a bar on top. If there's a 0, write the variable without a bar on top. It's the opposite of minterms or sum of products. So A bar or B bar or C bar, that's that rectangle there. Got one more rectangle to go and we're done. So what is A in this broken rectangle? Yep, A does not matter. It's a 0 here, it's a 1 here. What about B? Yep, it's a 0 here, and it's a 0 down here, so B is equal to 0. What about C and D? Both of them? There we go. C equals 1, right? So we can put, little labels on top of these if we want. C is a 1 in this box. C is also a 1 in this box. So C is definitely a 1. And in this box, D is a 0. In this box, D is a 0. So D is a 0. So this is the expression B or C bar or D. So now we've got our 4 sum expressions, and so our final function is the product of these 4 sums. So it's A or C or D ANDed with A or B bar or C, ANDed with B or C bar or D, ANDed with A bar or B bar or C bar. And there's your product of sums simplified. Yeah.
Didn't you just have see the top left and top right?
Mm-hmm.
Wrap those around. And
Yes.
then on the bottom right, could have just connected the 2 zeros, and you would have excluded the doesn't matter.
Excellent. So we could have done this to pick up this 0 over here, and then we could have done these to pick up this 0, and we wouldn't have covered the don't care. And that would be a perfectly fine covering. I think it would be the same complexity, because we would end up with a 2x1 here instead of here, and then we'd end up with a 2x1 here instead of here. So I think we'd end up with the same number of rectangles of the same sizes, but we would not be covering this don't care. And that would be a perfectly fine maximal cover. And you'll get a different equation, but that would still be an AND of 4 sums, with each sum having three expressions. And sometimes we may find that one covering might give us multiple terms that have an A bar, whereas in this case we only had one term with an A bar. And maybe if every expression had an A bar in it, we could reduce the number of inverters that we need or something like that. Or if we could get rid of this A bar by doing a different covering, we wouldn't need to invert A, and we get one fewer inverter somewhere. This is a process that's pretty easy to teach a computer to do, and it's very algorithmic, right? And so a computer can use a K-map internally to simplify an equation. In practice, when we actually do circuit design as a job, we're usually not doing this stuff by hand. We usually have computers doing this work for us. And towards the end of this course, when we start working with FPGAs, field programmable gate arrays, we'll actually look inside some of the tools. We'll design a circuit using a language called Verilog, but we'll actually be able to see the K-maps that the software came up with, and the way it covered the rectangles, and the way it came up with a sum of products or product of sums to implement a solution. And so this is important for us to understand, and it helps reinforce the idea of min terms or max terms, and it gives us an application of adjacency theorem and so on and so forth. But ultimately, down the road towards the end of the course, we'll switch to letting computers do this for us, except for exams and homeworks. All right, good. Other questions? So this is what you need for question 10 in the homework, right? You're trying to find a product of some expression for the following Boolean function. So you're given this function as a sum of products. First thing you can do is fill in a truth table, right? And this truth table is going to have ones in a few rows. This row, this row, this row, this row, and this is going to correspond to 2 rows, right? A, B bar, D, C doesn't matter. So you're going to end up with 6 ones in your truth table, which means 10 zeros. So then when you try to do the POS minimization with the K-map, you're going to have 10 zeros that you need to cover. And having lots of zeros, is potentially concerning, but if you have lots of zeros, you got lots of potential to cover big chunks of zeros with rectangles or ones, whatever you're covering. All right, let's look at some more extreme versions of K-maps, and let's stick with sum of products, because that's the more typical use case is when we're trying to do a sum of products, and so we're covering ones. And suppose your ones end up like this. How would I cover those ones with rectangles using our rules?
Well, you can do 2 by 4, right?
Yeah, I can do a big old rectangle like this.
Right.
And so A could be a 0 up here or a 1 down here, so A doesn't matter. B could be a 0 here, or it could be a 1 here or here, so B doesn't matter. C could be a 0 here or here, C has got to be a 0. And D could be a 0 in any of these or 1 in any of these, so D doesn't matter. So there's a really simple expression for this rectangle, it's just C bar. Well, what does our truth table look like? For this covering of rectangles, so we've got 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. This is a truth table that would correspond to this covering. And if you look at all the cases where your output is a 1, those are exactly the cases where your input C is a 0. And anytime C is a 1, your output is a 0. So this is just a big overgrown inverter. Right? It pays no attention to what A, B, or D are doing. It simply looks at C, and if C is a 0, it outputs a 1. If C is a 1, it outputs a 0. So the whole equation for this truth table would just be F equals C bar. And that pops out really quickly from just looking at this K-map and covering those ones. So that's a little bit more extreme of an example. What if you have all ones in every cell? How do you cover those with a rectangle?
Just a 4 by 4.
Yeah, big old 4x4. That's our best possible cover. And if I look at the values of A, B, C, and D, none of them matter. Because if A is, if I look at these, A is a 0. If I look at these, A is a 1. A doesn't matter. Here B is a 0, here B is a 1, B doesn't matter. C is a 0 or a 1, C doesn't matter. D is a 1 or a 0, D doesn't matter. So the output of this function is independent of A, B, C, or D. And in fact, the output is just, f equals 1. And that's a truth table with a 1 everywhere. The other extreme of the same flavor is where you don't have any 1s anywhere in sight. And so I have no rectangles covering any 1s. And so what is my expression for f? Well, it's independent of a, b, c, and d again, but in this case my function is just f equals 0. And the fact that I don't have any 1s in here means that, every output in every row of my truth table was a 0. Well, this is just the nope function, right? It just says nope, nope, nope. So it's always a 0. All right, what about if my truth table produces the following K-map? Let's put a 1 here, and let's put a 1 here. So now I'm looking at 0, 1, 1, 0, and 1, 1, 0, 1. So I've got a 1 here, and a 1 here, and a 0 everywhere else. And my K-map ends up looking like this. How can I cover the 1s of this K-map? What am I going to end up with? Two single blocks. So 1 by 1 there and a 1 by 1 there. And what's the product term corresponding to this first block? So what's the value of A do in this block? It's got to be 1, right? Because there's only one block in there, and A is equal to 1. And similarly, B is 1, and C is 0, and D is 1. And so the product term corresponding to this is A, B, C bar, D. And this 1 by 1 rectangle, A is a 0, B is a 1, C is a 1, D is a 0, so that's the product term, A bar, B, C, D bar. And if I OR those together, I get F equals A, B, C bar, D, or A bar, B, C, D bar. And guess what? That's the unsimplified sum of products that I would get in Engineering 120 from looking at the truth table. I'd write the min term for this row, which is A bar, B, C, D bar. Did I put this in the wrong spot? Yeah, A bar, B, C, D bar. And I'd write the min term for this, which is A, B, C bar, D. And I would OR those together. So in some cases, our K-map will not simplify our expression. We'll end up with exactly the same thing that we had if we had just written, a sum of products from the truth table. And that's happening when you write down your 1s and you try to cover it, and all you get are these 1 by 1 covers. So somebody asked, can you factor a b out of the expression? Would that be a simplification? It would, but you would not end up with a sum of products anymore. But, you know, if I was actually building this, I could do this. And that will give me a simpler circuit, because now I'm using 3 input AND gates. I'm still ORing them together, and I'm going to use one more 2 input AND gate to take this and produce my output value. So that's simpler. But it's no longer a sum of products. It's a product of a sum of products and something else. But if you were actually building the circuit, yeah, you would definitely want to do that, because that's going to be simpler components and easier to wire and so on and so forth. All right, let's go to the extreme extremes. You're going to get really good at drawing these pictures. Oh, we are just about out of time. By which I mean we're actually out of time. But let me just show you. So think about this one, right? Think about a truth table that ends up with this K-map, how you would cover it. We'll talk about that on Monday. And this will take us into another aspect of this, which is exclusive ORs. But yeah, the checkerboard is not your friend. So think about this for a minute or two offline. How would you cover this by rectangles? What would you end up with? And it's not a pretty answer. All right, we're 5 minutes past. I'll take off now. Have a great rest of the week, great weekend. I'll see you in lab and or office hours the rest of the week. Otherwise, I'll see you Monday in class. Take care.
Awesome. Have a great one.
Thanks, you too.